All right, so welcome. We're going to be talking about MRI magic tricks. So I'm Charlie Sum on Twitter. Full name's Charlie Somerville. You should follow me if you like seeing stuff like this. And I need to get a really big number next to my name on twitter.com. That would make me happy. Anyway, so as Josh mentioned, I am on Ruby core. I contribute to Ruby, a few performance patches here and there, a bit of bug fixes. And I also work at GitHub on the GitHub systems team. So as part of my work there, I get to spend a lot of time in the depths of the Ruby VM, looking into really weird behavior and figuring out how we can make Ruby faster for large production Rails apps. So let's begin. In this talk, we're going to talk about 3 different MRI bugs. And we're going to talk about how we can actually take advantage of these bugs in MRI to really push the limits of the Ruby language. So we can do things that you never thought were possible in Ruby. And I'd just like to mention that these bugs are totally specific to MRI. They won't affect other implementations. So if you're running JRuby or Rubinius, then you've got nothing to worry about. And in fact, even if you're running a recent version of MRI, you should be fine. And I'd just like to give a bit of a disclaimer that this talk doesn't contain any useful information. So if you're here to sort of grow as a developer and learn some things that you can actually, use at work, then you're in the wrong talk. So don't try this at home. And certainly do not try anything I'm about to talk about in production. So with that out of the way, let's get cracking. So the first trick I'd like to talk about is something called the frozen core. So there's a handful of hidden secret methods in MRI that are actually called internally by the virtual machine. And all these methods are on a hidden class called RubyVM frozen core. And the class doesn't officially exist. So if you try and access it from an IRB, for instance, you're just going to get a name error. So it's not actually exposed to Rubyland. But it does indeed exist, and here's the C code inside MRI that actually creates this class. So there's a bunch of methods, and it's all hidden from userland. And you can see an example of it being used in method definitions, for instance. So here's the instruction sequence dump for just def foo end. And you can see that there's 2 instruction sequences which are basically a listing of bytecode for the Ruby VM. And to define a method, you can see that it actually calls a method called core hash define method. So when you type some code like this, def my method 1 + 2, how that actually works in Ruby is that that's actually a method call against a frozen core object. It passes the class that you're defining the method against, it passes the method name, and then it passes an instruction sequence. Here I've used a lambda, but this is loosely what happens. So there's a whole bunch of methods living on the frozen core class. Here's a list of all of them, and I've sort of roughly translated them into how they appear in Rubyland. So whenever you use the method alias syntax, that's a method call internally to Corset method alias. So is aliasing a global variable, undefing a method, defining a singleton method, using the end syntax, creating a literal hash, splatting a hash in 2.0 and above, and using the 1.9 stabby lambda syntax. So as I said before, the RubyVM frozen core class doesn't actually exist. So if we want to start messing with it and really seeing what we can do with it and how we can break Ruby, then we're going to have to manually search for it with heuristics. So in the code dump I showed before that actually creates this class, we can see that it's commented, it says frozen core hidden, and it creates a new class inheriting from basic object, and it sets the flags to TI class, which is basically a way for the MRI internals to hide an object. So you won't be able to see it when you go object space.each object if you've played with that before. It just won't show up. But if we look up a bit, then we can see that there is a class that's exposed to Ruby called RubyVM. which is defined just before. And due to how the Ruby garbage collector works, objects that are allocated close to each other in terms of time often have memory addresses that are close to each other. So we can actually use this fact to sort of try and grab onto this frozen core object that isn't supposed to be exposed. So we grab the object ID of the Ruby VM class, and we can see that that's a big scary pointer-looking thing. And we can basically get a whole bunch of pointers that are within about a kilobyte of that pointer. And then we can use objectspace.id2ref to turn that integer into an object. And that'll raise an exception if we pass it an invalid object ID. So we do what most Rubyists do when we see an exception and just stick a rescue nil. So we've got a bunch of objects there, lots of fixed arms, a couple of floats, a couple of real objects like that string that just appears there. But what we're looking for a class. So we can grep for a class, and we see a bunch of sort of internal classes. We see thread singleton class, we see RubyVM env, which I'm not sure what it does, and a whole bunch of different interesting looking classes. But that class in the middle that doesn't have a name, that looks interesting to me, because frozen core is never given a name, it's never assigned to a constant. So this fits the bill for what we're looking for. And we can confirm this by just doing a find and looking for a class that actually has a method called core hash define method. And indeed, this is the class we're looking for. So we can just stick it on RubyVM, we can give it a name, and we can start messing with it. But this is just the class, so if we want to actually call any methods against it, we need to grab onto an instance of it. We can't call new against it because as a side effect of the trick that Ruby uses to hide it, it actually appears as a singleton class, so we can't just create a new instance. So we're going to have to use more hacks to actually grab onto an instance. So there's one single instance of this class living in the virtual machine. And what we can do is we can redefine the lambda method on the frozen core. And then we can use the lambda syntax to grab onto an instance of the frozen core. So that stabby lambda syntax will actually call a method against the frozen core instance called lambda. We've redefined that method just to return self, and all of a sudden we've got an instance of that class, and we can verify that it is indeed what we're looking for. But of course, this is a whole bunch of shit work, and we don't want to do this every single time we want to do this thing. Imagine if every single Rails app you had to stick this in an initializer. It's just no fun. So I made a gem, you can stick it in your gem file. This finds the frozen core class, it sticks it on RubyVM frozen core, and it gives you RubyVM frozen core.instance, and you can use that from anywhere to grab onto an instance of this internal hidden class. So as an example of what we can do with it, let's look at the syntax for aliasing a global variable to another name. We can assign a global variable called $A to 123. We can alias that to the name B, and then we can see that when we try and use $B, we get 123 again. We can do the same thing, except we can send the core set variable alias method to the frozen core, and we can pass it the new name of the global variable and the old name, and that works as expected. We can also override the hash syntax to actually reverse the members if we want. So when you actually use a hash literal, that is actually just a method call internally. So we can override that, we can reverse the array, and then pass that into hash, and all our keys are backwards. We can hook into method definitions, since that's just a method call against a class. So in this example, we're redefining core hash define method, and what we're doing is we're just dumping all the method definitions that go on. So in this case, we can see that when we type def fooend, it calls into our method that we've redefined, and it logs a nice message. Now we can also use this trick to backport the new, one of my favorite new features in Ruby 2.1, which is where method definitions will actually return the symbol of the method name that you've defined. So this is really useful if you want to do things with, it's sort of Ruby's answer to decorators. So you can write private def my method, protected def my method, probably public static void my method if you want. But we can backport this just by overriding core hash define method. And what we're doing is we're grabbing an instance of the frozen core, we're defining the method, we're making sure we're in the right scope first, and then we can just return the right name, And you can see that when you type def foo end, we actually get a symbol foo back. But there's danger here because the frozen core methods assume that they're only ever called by MRI internals. A lot of the code is written with the assumption that the only code that's ever going to call these methods is MRI internals, so there's very little in the way of actual error checking, which means that they can easily crash if you call them the wrong way. So here's an instance of the C code behind the hash from array method. So what this method does is, as I showed before, when you use a hash literal, this just translates into a method call to this method internally. And it does some stuff. It basically loops over the array and sets hash elements for each pair in the array. But take special note of this assertion that's there. So this is one bit of error checking. It actually makes sure that the length of the array is divisible by 2. And we can see if we pass an array that doesn't have an even number of elements, then we get an assertion failure and Ruby crashes. Another example is in Corset method Alias, where this is basically the method behind the Alias syntax, where if you have 2 symbol names and a class, it'll basically create an alias for that method. So this assumes it's being called with a class and 2 symbols. And so if you call it with something that's not a class, then you might get a weird error. And this is actually an error that Ruby will print out if you try and call this method with a fixed time. It'll say, runtime error can't modify frozen something. And if you call it with a bona fide object, then it'll just straight up crash. So that brings me to my second magic trick, which is changing superclasses. So how many times have you been working on a Rails app and you've run into a bug with the Rails reloader, where for some reason or other, it's thinking that you've already defined a class, you're trying to give this class a different superclass, and it's complaining that there's a superclass mismatch. Has anyone run into that before? Yeah, so you can work around this with this little trick. So let's take a look at how duplicating a class works. So we can call .dup on any object in Ruby, and we actually get a new copy of that object back. And lots of the core classes in Ruby are actually specially implemented so that they properly copy over a bunch of their internal state. And this is true for class. So we can dup the string class, and we can see that when we dup the string class, it keeps the same ancestry chain. So in the first case, we're just calling ancestors on string, and we get string and then all its superclasses and modules that it includes. And then if we dup that, we see that we get a new class as the first element in the ancestry tree, but then all the other classes are just the same. They're just copied over. So when I saw this, I thought, that's a bit interesting. I wonder how that works. So I dived into the code implementing object dup. And it basically, this is a loose re-implementation of object dup in Ruby. So it basically allocates a raw instance of the class, and then it calls initialize copy and passes in the old object, and then it returns the new object. So I looked at this and I thought that the code that is copying over the ancestry must be in initialize copy. So I looked at the C code behind class initialize copy, and this is it. It's pretty easy to understand. It's pretty high level. So basically, it'll raise an exception if you're trying to duplicate basic object. It'll raise an exception if you're trying to initialize a class that has already been initialized. And it'll raise an exception if you're trying to duplicate a singleton class. But if all of those checks pass, then it just calls onto mod init copy, which is basically a supercall in C. And then RB mod init copy, which is module's initialize copy method, calls object initialize copy, does some stuff, and then it actually copies the superclass over. So we can see this by calling class.allocate, and it's just got an empty ancestry chain since it's completely uninitialized. And then we can send initialize copy to that, and we can pass in an existing class, and we can see that it actually just copies over the ancestry tree. We can pass in, because it actually copies the superclasses, if we want to set this class's superclass to another class, we have to create a new class, which is a subclass of the new target superclass, and then pass that in. And then we can see that this actually correctly makes K a subclass of string. But of course, if we don't use allocate and we just use an already initialized class, when we send initialized copy to that class, we get an exception with already initialized class. And this is due to this little bit of error checking here. But if you might have noticed that all these error checks are performed in class init copy. So these error checks are performed in class init copy, and then it forwards on to module initialized copy, where there aren't actually any error checks at all. So of course, we can redefine class initialized copy to just perform an empty supercall, and then we can get our K class, we can send initialized copy to it with a subclass of string, and all of a sudden, the ancestry chain has been rewritten. So this is an already initialized class. We might already have objects of it, and then we can basically change its ancestry chain, which means that any methods called against it now follow a different chain of lookup. And another way of doing this without monkey patching class is to just grab onto a raw method handle for module initialize copy. We can bind that to K since it's a subclass, since class is a subclass of module, and then call it. So this is a useful monkey patch. Another useful monkey patch that we can basically build on top of this is superclass equal. So if you've looked at the superclass method in Ruby before, you might have noticed that there's no writer counterpart. So we can define our own. So this basically lets us say any class dot superclass equals another class, and it'll change the superclass of the class in question. So if we have two classes A and B, and we have another class C which inherits from A, we can look at the ancestry chain for the C class, and we can see that it's C, which inherits from A, which inherits from object, which mixes in kernel, which an object inherits from basic object. And then we can call C.superclass equals B, and if we call ancestors again, we can see that all of a sudden we've got a completely different ancestry chain. We can actually change the superclasses of built-in classes, so if we have a string hello world, we can call 2s on it and get back hello world, but if we change the superclass of string to fixed num, when we call 2s, we get a string representation of the pointer value of that string. Although if you try and do it the other way around, then you'll just run into a seg fault. And I might note that this particular bug only affects Ruby 193. It was fixed in a certain patch level. I'm not quite sure which patch level it was fixed in. But if you're running 2.0 or above, then sorry, you can't use this trick. You're going to have to find a better solution to your problems. But if you do accidentally crash Ruby, which we all do from time to time, then you're in luck, because my third magic trick I'm going to show you actually lets us rescue from segmentation faults. So I'm sure you've all seen this screen before. You've booted up your else app, you use some dodgy C extension, and it's just gone kaput. And you see a big scary segmentation fault. There's backtraces. There's all sorts of useful debugging information in it. But one of the interesting bits of debugging information is the list of loaded features. So loaded features are all the files and C extensions that you've actually required into your Ruby process. And I thought that was interesting because the loaded features array is actually exposed to RubyLand through the $loaded features global variable. So somehow this is looping over an array that's exposed to RubyLand and printing all these strings out. So if we look at this code, this is part of the segmentation fault handler. This prints out the header loaded features, and then for each element in the array with this basic C for loop, it calls string value cstr, RRA pointer, and basically grabs each element of that array and prints it to the screen. But this particular expression is interesting. So let's dive a little bit more into string value cstr itself. So it's a C macro that just forwards a call onto RB string value cstr, which looks like this. It converts the object you pass it to a string and then does some basic checking. So if the string contains a null byte, then it'll raise an exception. Otherwise, it'll do some fix-ups, it'll actually append the null byte on the end to make it a valid C string, and it'll return it. So if we look into this RB string value call a little more, we see that it looks a little bit like this. So RB string value, we check the type of the object we're passed in, and if it's not a T string, it'll actually convert the object to a string. And it does this with another C function, which basically calls the toStr method on every single object in the loaded features array before dumping it to the screen. Which means that if we put, say, a fixed num into the loaded features array and then force a seg fault by sending ourselves sigsegv, we can see that while Ruby is dumping all its segmentation fault debugging information, it actually dies with an unhandled exception, saying that it can't convert the fixed num into a string. So this is interesting because it's obviously calling methods on objects that we can access from Rubyland during the seg fault. So if we define an object and we override the toStr method on it to put a method to the screen and then exit, and then we put that into the loaded features array, we can see that while Ruby is crashing, while it's dumping the loaded features, it'll actually call our method and we have a chance to dump a message to the screen and then exit. So we can use the same trick to raise a segmentation fault exception instead. So we can override toStr and we can raise a segmentation fault. We can stick that into the loaded features array, and then we can call sigsegv. We can send sigsegv to the current process. And then while Ruby's crashing, it'll raise a segmentation fault exception, which we can just wrap in a begin rescue end and keep on rolling. So we've covered 3 magic tricks. We've covered the frozen core, which basically lets us dive into the internals of Ruby and redefine even core syntax. We've looked at how we can change superclasses, and we've looked into how we can clean up after ourselves after doing the first 2 magic tricks and actually rescue segmentation faults. So that's it. Thanks for watching, and I hope you learnt a little bit about Ruby and learnt some things that hopefully you never try.
Awesome, thank you very much, Charlie. Now we've actually got quite a bit of extra time because he likes to talk fast about nothing. So do we have any questions? We've got one.
Yep.
Run it! Run it! Run!
Where are you?
So, sorry, I know that segmentation fault thing was done in jest slightly, but would it be a crazy idea if the MRI guys actually allowed us to catch segmentation faults?
So basically, yes. I mean, if there's a segmentation fault should never happen in Ruby. So if it does, it's a sign that you've got a misbehaving C extension or that there's a bug in Ruby itself. So if a segmentation fault happens, then that basically means that there's some sort of state in your Ruby process that's corrupted and it's not safe to continue execution. When I was actually putting this talk together, I was playing around with the segmentation fault stuff. And I found that even though you could raise an exception out of the seg fault handler, Ruby still thought it was inside the segmentation fault handler, even after it had thrown an exception out, because it's not designed to exit the segmentation fault handler. So the second seg fault you receive after doing that trick will actually just hard crash your program. You won't even get a chance to override it or intercept it. Any other questions? Oh, yeah.
Hi, be honest, have you used any of this in prod?
No, but I did recommend a guy in ISE to do it once. Who was having the exact superclass issue with his app on Heroku. So I gave him this trick and he was on his way. Any other questions?
Yep. Oh.
When you converted a fixed num to a string and got a crash,
Yep.
might you have been able to lay out a structure and convert it to a string and use that to actually poke it arbitrarily to memory? And is there a security hole there?
Definitely. So that was actually something I was playing with, and there's another one that didn't quite make it into the talk, where you could actually write an arbitrary integer to any address in the process. But yeah, so definitely there's lots of places in MRI where it's not quite type safe. So it is possible to give it a bit of memory that isn't what it's expecting and have it write to arbitrary memory. Definitely. Yeah.
Hi, I was wondering, how can I join PHP core and how many commits do I need?
I'm not even going to dignify that with a response.
All right, so what if, this is like with your extending superclasses, what
Yep.
if you have three, A, B, and C, and A superclasses B, and B superclasses C, and C superclasses A?
So you've got a infinite superclass
Yeah,
chain.
what happens when you call ancestors?
Your Ruby process will just hang forever and use all the memory on your system. It will work as long as you never call an undefined method. If you do that, then it'll loop forever as well.
Is that another good production tip for IRC?
Yeah, don't do that.
Any other questions?
Since GitHub got their own Ruby version
Yep.
maintained, have you done any stuff like this on the GitHub version?
Fixed any of these bugs or introduced any of these bugs? Or?
Yes.
So all of these, I should have mentioned before, but all of these bugs are fixed in the latest version. So if you're running 2.1, then you're affected by none of these. If you're running 2.0, then you're only affected by the frozen core one. So yeah, we're running 2.1, so we're not affected by any of them.
Hey, this is slightly broader, but why do we have frozen core now anyway in Ruby? Why is some of it, like what's the border these days between what's directly in C and what's in like this little core thing in between an actual Ruby land?
Yeah, so that's a really interesting question. So I think the idea behind extracting this stuff behind a method call is to keep the core VM itself small. But I mean, at the same time, I'm probably not the best person to ask that question of because I wasn't involved in the actual design of the VM. But I would imagine it's something to do with keeping the core of it small.
Any questions from this side? We still love you. Anyone? Anyone? No? Any other last minute MRI, what the fuck can I do with MRI questions? No? Okay. Oh,
One more.
cool.
Is it possible to disable the global VM lock?
This is always a popular question. It's possible to disable it, but the problem with that is that there's a lot of C code in MRI internally that is written with the assumption that there is the GVL, so it's probably going to be fairly unstable if you did that.
What kind of interesting crashes can you get there?
Possibly very hard to debug crashes. Whenever you're playing with threading, you never want to deal with debugging it.
Okay. Thank you very much, Charlie.